In an earlier video, we started talking about bomb calorimetry and how it could be used to find the internal energy of the system. So we did this by holding our volume constant, and that allowed us to only find the heat released by the system rather than worrying about also dealing with work. So we use a similar method to find the enthalpy of reaction, and that method that we're going to use is coffee cup calorimetry. And again, that's going to allow us to find the enthalpy of reaction, which is delta H of reaction. And the reason that we use coffee cups is because styrofoam coffee cups are excellent insulators, and that makes them a useful and affordable material for constant pressure calorimetry. So the reason we want to be at constant pressure to find the enthalpy of reaction is that delta H equals Q at constant pressure. So remember that Q with a subscript P means Q at constant pressure. So by finding the heat that is exchanged by the system and the surroundings at constant pressure, we'll also be able to find delta H. So this is our calorimeter. Let's see if I can move this up for you. Yeah, so that's our calorimeter. And as you can see, it's made of 2 styrofoam coffee cups with some kind of insulating lid, something to stir the solution, and a thermometer to measure the temperature. Notice how even though there is a lid, notice how it's loose fitting. It's not completely sealed and it's not pressurized. So what that does is it's pretty much open to the atmosphere, which keeps it at constant atmospheric pressure. With this calorimeter, we're also measuring the heat exchange between the system and the surroundings, just like we were with the bomb calorimeter, except this time, our entire calorimeter is not considered the surroundings. We're only going to look at the solution as our surroundings. So again, we're not looking at the whole calorimeter as our surroundings. Again, because that's a really good insulator, we're treating the heat that's exchanged with the calorimeter itself as negligible. So that also means that our heat capacity of the calorimeter is also negligible. So what are we going to use for our C value when we solve these equations? Remember, we're still using the same equation that we've been using, the Q equals mc delta T, except this time, instead of the heat capacity of the calorimeter, we're going to use the specific heat capacity of water because we're going to be working mostly with aqueous solutions. And this value is 4.18 joules per grams times degrees C. So you should get to know that value. You're going to end up using it quite a bit over these next couple of weeks. So let's go ahead and do a problem. Okay, so if you'd like, go ahead and pause the video here to give yourself a chance to copy down this problem. So we have 0.185 grams of magnesium metal is combined with enough HCl to make 100.0 milliliters of solution in a coffee cup calorimeter. The HCl is sufficiently concentrated so that the magnesium completely reacts. The temperature of the solution rises from 25.6 degrees C to 32.8 degrees C as a result of the reaction. Find delta H of reaction for the reaction. The density of water is 1.00 grams per milliliter, and the specific heat capacity of water is 4.18 joules joules per grams times degrees C. Okay, so what are we trying to find? We're trying to find delta H of reaction. And what units are we going to use? Well, delta H of reaction is usually in either joules or kilojoules. It doesn't specify here in this problem, so we can start with joules. If the number seems more appropriate for kilojoules, we can switch to that also. I would accept either one if the problem does not specify. The information we know that we have 0.158 grams of magnesium. We know that we have 100.0 milliliters of solution. We know our T initial, our initial temperature, which is 25.6 degrees C. We have our final temperature, which is 32.8 degrees C. We have our density of water, which is 1.00 grams per milliliter. And we have our heat capacity of water, which is 4.18 joules per gram times degree C. Okay, so that's a lot of information. And so we need to come up with a good strategy for organizing how we're going to solve this. So we know it's a calorimetry problem. We're going to use Q equals mc delta T. That's our heat transfer equation. So calorimetry is basically an organized experiment involving heat transfer. So that's why we're going to be using a heat transfer equation. And we're going to need to find Q because we know that delta H is equal to Q at constant pressure. So in order to find delta H, we need to find Q. So that's going to be what we're solving for. So we need the mass of solution, we already have the specific heat capacity. We just use water, the specific heat capacity of water, because the solution is aqueous. And then we don't have our delta T, but we can very easily find our delta T using the information that was given. So let's go ahead and start solving this problem, trying to figure out the information that we already know we're going to need to find. Okay, so let's start with our M value. We know that we need the mass of solution. Well, we don't have mass, but we have volume. We also have the density of the solution. And we know from previous chapters that we can use density as a conversion unit, or a conversion factor. So we can just do a conversion to get M. Oops, here we go. To get mass of solution, we know that we have 100.0 milliliters of solution. And we know that we have 1.00 gram per 1 milliliter. Milliliters will cancel with milliliters. So that is going to give us 100.0 grams of solution. So there we go, we found our M. C we already have. now we need to find our delta T. So to get delta T, we want to do T final minus T initial. Our T final is 32.8 degrees C, and then subtract 25.6 degrees C. And that's going to give us 7.2 degrees C. So notice the significant figures there. It's subtraction, so when we're doing significant figures rules for subtraction, we go by place value, not number of sig figs. So yes, we have a 3 sig fig number. Oops. We have a 3 sig fig number and a 3 sig fig number. But it doesn't matter the number of sig figs, it only matters the place value that it ends in. So that's why we end in the 10th place here, and it's totally okay that we end up with a 2 sig fig number for this calculation, even though both of our starting values had 3. So we can input our 7.2 degrees C into our equation. So when we solve that, we get 3009.6 joules. And so what is this value exactly? This value is actually the Q of the surroundings, because that's really what we measured. We measured the temperature of the solution. The solution is considered the surroundings. We know that in the end, our answer is going to have 2 sig figs. So I'll just keep that underlined for now, just so we remember. But we don't really care about the Q of the surroundings. What we really want is the Q of our system. And our system is our reaction. So we know that the Q of the system is equal to the opposite of Q of the surroundings. And we know that Q of reaction is our system, and our solution is our surroundings. So that means that our Q of reaction is going to equal to negative 3009.6 joules. Okay, so that's where we are so far. We found our Q of reaction. And we know that delta H is equal to Q at constant pressure. So in this reaction, this is the number of joules we formed. This was our heat that was, notice it was released, it's negative, so the amount of heat that was released by this reaction. But also notice that this is the amount of heat that was released when a very specific amount of reactant, of both of the reactants reacted together. So this isn't a general for any time you do this reaction. This value is dependent on the amount of reactants that you had. So in order to figure out our value, we're going to have to put the Q of the reaction over the moles of reactant. So specifically here, this is going to be the moles of our limiting reactant. So far, we already have our Q. Now we need to figure out what is, like how many moles of our reactant did we have. Well, let's look back at the problem. Because here we need to figure out, we have two reactants. Which one do we even want to use? So in our problem, it says that the HCl is sufficiently concentrated so that the magnesium completely reacts. If the magnesium is reacting completely, that means that that is our limiting reagent, so that's going to be the moles of reactant that we use. Oops. So magnesium is the limiting reagent. Which means we need to find the moles used. So we can do that. We're given the mass of the magnesium, so we can do that stoichiometry. .158 grams of magnesium. Then we look at the periodic table to see what is the molar mass of magnesium metal, and it is 24.305 grams of magnesium per 1 mole. And when we solve that, we get 6.50 times 10 to the negative third moles of magnesium. So now that we have our moles of magnesium, we can input that back into our equation. So 6.50 times 10 to the negative third moles of magnesium. And now we get our delta H is negative 4.6 times 10 to the 5th joules per mole. Well, the units of delta H of a reaction that we usually want are just joules or kilojoules. So we want just energy units. We don't really want it in per mole. So what we need to do is we somehow need to multiply by moles in order to get rid of that mole unit right there. So how do you think we're going to do that? Well, just like one of the other problems, we're going to need our molar ratios. So in order to get the molar ratios, we need our balanced equation. So it's basically really, really difficult, if not impossible, to do these problems without our balanced chemical equation. So let's go ahead and write that. So if you want, you can pause the video here and try to write the balanced equation yourself, since we have been practicing that over the past few weeks, and then unpause and see if you got the correct answer. So the correct balanced equation for this problem is you have magnesium solid plus 2 HCl, and it's aqueous, it's an aqueous solution, yields MgCl2. Now remember your solubility rules. MgCl2 is aqueous, plus H2 gas. So now what we have to do is we have to multiply by our molar ratios. Remember, when we don't have a number there, it's just 1. And so since magnesium, again, it's our limiting reagent, so we're going to use the molar ratio of magnesium. So for delta H of reaction, we get negative 4.6 times 10 to the 5th joules per mole times 1 mole of magnesium, and again this comes from the molar ratio in the equation, and that's going to allow us to cancel out moles so that delta H of reaction is going to equal negative 4.6 times 10 to the 5th joules. If you would like to put this in kilojoules, all you have to do is move the decimal point so that you get negative 4.6 times 10 to the 2nd kilojoules. And that's how you solve a coffee cup calorimetry problem.